So where we ended was talking a little bit about density. So before we push into this a little bit more, let's consider some of the units that we could look at for density. So we've got three phases written or examples given for us. We've got ice, which is referencing solid H2O. We've got water, which is an attempt to reference liquid H2O. And then we have water vapor, which is gas H2O. And if we consider the units for density, like what units should we actually use? Well, if we take a look at the solid and the liquid, you'll note that we're actually specifying units for those. So our density, if you remember, is the relationship between mass and volume. And by definition, we kind of go as mass over volume, though really it doesn't matter. So when we're looking at units of mass, what unit should we pick? Well, clearly the unit that's being picked here is grams. And then the volume unit that's typically picked is actually milliliters, not necessarily centimeters cubed, but our textbook and this particular figure decided to use centimeters cubed. But as we talked about in an earlier class period or session, 1 centimeter cubed is by definition equal to 1 milliliter. So there's not a big difference there. So grams per milliliter. So if we go through and look at our solid, we're noticing that we're getting a value that is roughly equal to 1, or numerical value. If we look at water or liquid water, it's again value 1. So the question that's being asked kind of on this slide is, well, why did we pick the units of grams per milliliter? There were tons of other mass units we could have used. Kilograms per liter. We could have used or not an equals. We could have used tons per gallon. Okay, all of those represent masses and volumes. Why did we pick grams per milliliter to represent it? Okay, and it's a relatively simple answer that we've kind of pushed to in a lot of other cases. It's that our human brain is really petty and pathetic and can't deal with these big concepts. So we picked unit systems that allowed us to attach a numerical value in front that was relatively simple to deal with. So in this case, we're picking a number. Okay, so the unit we pick is such that the number that is associated with those units usually falls in the range between 1 and 10, because we have 10 fingers. So if we pick a unit system that gives us that, we're pretty happy. And so when we look at our solids and our liquids, it's great. Grams and milliliters works phenomenally well. But what happens when we move to a gas? Okay, well, if we represented the shape of these individual things, solids are all very, very closely packed. The liquids get a little bit more spaced out, but they're still, for the most part, pretty closely packed. When we move to a gas, there's virtually no contact space between these. Okay, so if that happens, then within that individual volume, if we're maintaining the same volume here, let's just assume that we're using milliliters, the mass amount is going to be astronomically low. So if we looked at a just random, I'm guessing at numbers here, we'd be looking at a mass that might be on the order of grams per milliliter. Okay, well, that value is now so low, okay, and I'm going to be a little bit less dramatic about it. That value is now so low that we don't really comprehend it so well. So because the units we picked were effectively arbitrary and designed to give us a numerical value that our brain could wrap around, we can now change the unit system into something that would allow us to understand it a little bit better. Okay, and to that end, if we converted this into scientific notation, 9.13 times 10 to the minus 3, because we shifted 3 places, and it's a number that's smaller than 1 grams per milliliter. Okay, again, we now have powers of 10. That's bad, but what we do remember, because I told you to memorize what our powers of 10 meant, is we now have 9.13 milligrams per milliliter. Okay, this takes that number out front and puts it on a scale that is somewhat similar to that 1 to 10 range. So we can change the unit system so that we get a number that's easier for our human brain to comprehend. So when we're thinking about our units for density, don't always zero in on the number. In fact, you shouldn't ever zero in on the number because that can be very misleading. Make sure that you're using the units associated with that number appropriately to interpret it. And if we clear everything away, what's going to end up happening is that if we look at our individual density units for our solids and our liquids, typically we're seeing grams per milliliter. For water vapor, we'll typically see grams, but now we see per liter. Okay, so we end up expanding the volume of our system instead of decreasing the mass. Okay, it gets this to the same concept. It's ultimately getting us a number that's within 1 to 10, okay, or ballpark within that range. To give you an idea, we can go ahead and take a look at some examples. Man, those are incredibly tiny. Apologize, I should have zoomed that in a little bit. But if we go through and look at our example solids, note they're reporting the units here in grams per milliliter. And take a look at the number. Roughly 1, 2, 3, 8, 11, 20. You might be, well, 20 is too big. We can't count that high. Ballpark. Okay, that's the intent, is to get us into a range that's reasonable. So most of our solid numerical values will fall in that range that works out well for grams per milliliter. If we go through and look at our liquids, you'll notice pretty much the same thing. Okay, they're falling in that probably 1 to 20 range. And again, the unit system that we're using is that gram per milliliter. Okay, what happens when we move up to gases? Take a look at those numbers. Those numbers are, again, still kind of in that 1 range. They're all pretty low, okay, which makes sense. Gases have lower densities. But you might be like, well, numerically, those aren't all that different from our solids and our liquids. But take a look at the unit. They shifted the unit, okay, to account for that discrepancy in the numerical values. Okay? So, again, our gases, typically grams per liter. Our solids and liquids will typically be grams per milliliter. And a lot of that has to do with how we're trying to represent those numerical values and getting them into systems that we can deal with. If we go through and look at examples on how we can manipulate or use this, say on an exam question, we could go through and say, for object solid 2, explain its density. Okay, so you might be, well, there's no numerical values. We don't need numerical values to do an explanation of the density. We know S2 sunk, okay, or fell lower than S1. Okay, well, because it is more dense, it'll fall lower in our sequence. So our highest density substances are at the bottom, and our lowest densities are at the top, okay, or they float. And this is how we take advantage of it. We're usually using density to come up with buoyancies and things like that. Okay, so you could come up with relative densities. So in this case, S2 is a lower density than S1. So we could say S1's density is greater than S2. And we could even say that S2's density is lower than L2 because it is on top of liquid 2. Okay? Just to give you an idea on exam questions, the exam question is almost undoubtedly going to drop this all into a text situation. As soon as it goes into a text situation, it becomes a little bit more difficult to interpret. And of course, I've got an alarm going off, so we'll just throw that away. Putting it into a text situation makes it more difficult to interpret. But what you should ultimately do is, as you read the text, build a diagram that's roughly this. Okay? Now you have the way to be able to interpret and answer a multiple choice question. Because not only are you going to have to deal with that text, but you're probably going to be given them out of order to make it a little bit more challenging to interpret and answer those questions. Okay, so calculations of densities. How do we go through and do it? one argument is that you would memorize the formula density is mass over volume. My argument is you don't have to do that. Read the question. What is the question asking you to solve for? So if we start off, the first thing we're being asked to solve for is grams per centimeter cubed. So if I follow the process that I've talked about in class, we do grams per centimeter cubed as our answer. And now we go back and look at our given information. Well, I'm given that I have a 224.50 gram block, and I'm given that I have 10.0 centimeters cubed. So what can I do with that? Well, I would now go through and put that information into my solve. I want the mass in the numerator, 224.50 grams. And why would I place it in the numerator? Well, look at where mass shows up in my answer. My answer shows grams in the numerator. I'm going to put this over 1 because this is a single piece of information. Okay? I don't want to combine pieces of information because the only reason I can do that is if I know an extra formula to do that. So I don't bother to memorize a formula, and because of that, I only want to insert it as a single value. The next piece of information that I have is that I have 10.0 centimeters cubed. Well, again, I would look at my answer. Centimeters cubed is my volume placed in the denominator, so I'm going to place centimeters cubed in the denominator, 10.0 centimeters cubed. What do I want to place in the numerator? Just 1, because again, the only piece of information I'm given is this 10.0 centimeters cubed. I'm using my answer to tell me where to place that numerical value. In the remaining location, I don't want to put anything, okay? Because I don't want to change my piece of information. Now what can I go through and do is I can go through and solve. I can enter this into the calculator, and I would get, assuming I do my math right, for an answer to 22.450 grams per centimeter cubed. Okay? If this is a question on a test, I'm now wrong. Okay? And almost guaranteed, this answer shows up as a multiple choice answer. And for those of you being like, well, isn't that how you divide by 10? Yeah, it is. But remember, in science, we have to abide by significant figure rules. We haven't correctly accounted for sig figs. Okay? The first piece of information, our blue one had 3 sig figs. And our green one had, 5 significant figures. Because our operation is multiplication and division, I'm only allowed to keep the fewest number of sig figs, so 3. I can go to my answer and underline. My first insignificant digit is 5 or larger, so I'm going to add 1 to the previous one, and my answer becomes 22.5 grams per centimeter cubed. If this was a question that was testing on or testing on sig figs, I can almost guarantee both of those answers would show up. And so I'll give you an idea of some answers that I can think of off the top of my head that would be there. And I can't do the other division in my head, 10 divided by 224.50. So if we go through and look at these answer choices, number 1, this is a sig fig issue. Okay, B was correct. Okay, what happened with C? Well, if we look at C, what happened is we did the wrong math operator. Okay, and you might ask, well, why would that answer choice even be there? That answer choice is there because if you don't know what you're doing, you will just jam numbers together and ta-da, it shows up on the calculator. Okay, so it's direct evidence that you don't know what you're doing. That's why it shows up as a math or as an answer choice. The same deal with D. It's the wrong math. It's the wrong process behind this. If your process is wrong, we'd better have an answer choice there to exploit your failures. Okay? And I know that sucks, but that's what has to happen. You have to prove your understanding. Okay? So, with that in mind, let's not clear all that away just quite yet. We'll let you look at it if you'd like. What I want you to go through and do is spend some time to get pounds per liter figured out. Okay? And I'm going to pause the video So all of this is going to be deleted. When we restart back up, we'll just see all of that work. No, we're going to talk through it. We'll talk through all of that work here in just a second. So I'm going to clear everything. So cleared all. Now what I want you to go through and do is pause the video. Okay, and seriously, pause the video. And I want you to go through and solve for this process, except now in pounds per liter. So again, pause. Did you pause it? Okay, I'm going to assume you've solved. So again, what I'm going to do is say what I want for an answer. I want pounds per liter in my answer. Something that can be useful is to acknowledge that pounds is a measure of mass and that liters is a measure of volume. That is entirely illegible, so I'm going to rewrite that. We're solving for pounds per liter. This is mass, and this is volume. That's not much more legible, but hopefully it's a little bit easier. Okay. I now want to go back to my given information and decide what I want to use. Okay. I'm for sure given this 224.50 grams. I'm for sure given this 10.0 centimeters cubed. Okay. What makes this question a little bit more challenging is that pounds and liters don't explicitly show up, and for those of you screaming about down below, hold up. Okay, don't explicitly show up in the given information. So how would I use that? Well, I'm going to use it pretty much the same way that I used in the other thing. The grams is a measure of mass, so as long as I know that information, and centimeters cubed is a measure of volume, so as long as I know that information, I can now use that to go through and set up my solve. I know that I need the mass in the numerator because look at my answer. Okay, so I'm going to start with grams in the numerator. The given information associated with that is 224.50. There's nothing else given with it, so this is one piece of information. Okay, and then I want my volume in the denominator, centimeters cubed, 10.01, right? So there we go. Again, another one piece. Okay. The beauty behind this process is that I can run all of the calculations at once in one single line. I'll try and break it up into steps here in a little bit, but I'm not going to talk through that. So I can now go through and evaluate. The first thing I can see is that grams is not pounds, or that's the first thing that I see. So what I'm going to do is target that. Okay. So minimally, I need grams to disappear from the left-hand side. So I'm going to place it in the denominator. And I also would like pounds to appear. So now I've got a conversion. This is a conversion factor I would like to have. So if I don't know, I've got to look. Okay, so this is where I could look to the front of the exam and hope that I see it. Okay, or look to the question. And there it is. It is given. 1 pound is equal to 454 grams. So where should I place the 1? That wasn't supposed to be a rhetorical question, but since there's no audience here, it makes it a bit difficult to do this. For those of you that said on top, you are incorrect. For those of you that said in the numerator, you are also incorrect. Okay? And for the rest of you being like, what the F? There's no other place to place it because it doesn't belong in the denominator. You're right, it doesn't belong in the denominator either. Okay? Where the 1 belongs is with pounds. Not on top, not on bottom. It belongs with the unit pounds. Okay? Associate your numbers with the unit, not the location. The location may change depending on the problem you're solving. The 454 now should go with grams, not on the bottom. Okay? Again, associate it with the unit. This is now a given piece of information. Again, one piece. You'll notice this one piece is different from the other one pieces we've used because this one piece has 2 units in it. It has both the pound and the gram. Okay, why am I allowed to combine it now? Because it was combined for me in the given information. Okay, that's when we can bring in 2 pieces at once. If we go through and look at our unit system, the grams cancel. I would now have pounds per centimeter cubed. I don't want centimeter cubed, so now I have to initiate the next conversion. In that conversion, what do I want to have happen? Well, I want centimeters cubed to disappear, and I want liters to appear. Well, just like we did with pounds and grams, we would look to our given information and hope we find something. Okay, and we do find something that relates centimeters cubed, but it doesn't relate it to to liters, which means the conversion factor that I'm hoping to find doesn't exist, at least explicitly, which means I'm going to have to go to a different conversion. I'm going to go centimeters cubed to milliliters because that's the information I've got. The numbers for that are 1 and 1. Again, that is one piece of information. Okay, that's going to clean up some things because centimeters cubed is now canceled, but now I've got milliliters. I don't want milliliters, so what do I have to do? I have to get rid of the milliliters unit, so I'm going to place it in the numerator so it cancels, and I want liters to appear in the denominator. That conversion factor is one that I expect you to know or to memorize. So again, this is now a memory piece. You would have to realize that milli means 10 to the negative 3. The power of 10 always goes with the core unit. And we now have our solve. Milliliters cancel, and we would be able to go through and enter this into a calculator and get a final answer. Because there can be some issues with entering things into the calculator, I'm going to calculate that in just a second. So my calculator spits out that answer in orange. I have to again recognize my sig fig rules. This came in as 3 sig figs. The red one came in as 5 sig figs, which means I can only use 3 sig figs. I can go through and underline 494. Since the first insignificant digit is less than 5, I do nothing, and my answer becomes 49.4, what is it, pounds per volume. That was nice. Pounds per liter. Okay, and we would now have my answer that I could then submit for my final thing, assuming I entered all those things in correctly, which I think I did. Okay, you should be able to confirm that. I am going to pause the video and then write out all the work for doing this individually in another version of this. Okay, a version that you might be more familiar with, and I'm going to tell you again and again and again, it's a bad idea to do this. Ta-da! This might be the work you have seen in the past for this kind of a problem. Again, bad work. There's multiple places that cause problems or that potentially cause problems. First and foremost, you'll notice that we actually get a slightly different answer here because we didn't account for rounding appropriately in this process. Another thing that will sometimes trip people up is that we're using, particularly if you're being asked to show your work, we've got an equals sign in there saying that this is an equality, and that's not an equality. Okay, lots of places where this calculation can go wrong. It is not recommended, but some people want to see it, so there it is. I think you're going to regret making the choice to keep doing calculations in this way, and you'll probably regret it within, I'm going to guess, an hour of lecture videos. Okay, with that, we'll go ahead and continue. Density is a unit factor, so yet another calculation that we could go through and run. I will kind of talk through this one really quickly as we go through and solve this. When we read through this question, we want the grams of acid. So I want grams as an answer. If we look to my given information, what given information do I have? I have 120, that's not 100, but that number, milliliters of acid. Okay, and then that density for the acid. Deciding which one to use first, my recommendation is to use the one that uses or that has the answer that you want in it. We want grams in it. If we take a look at our milliliters of acid, milliliters is not grams. It doesn't make sense to use that one first. However, grams is in the density given. Okay, so that would be grams per milliliter. Good idea to write it out again. 1.84 should be close to the unit that it's close to in the given information, and it's closest to the grams, which means the 1.84 should go next to the grams. The number next to 1 or milliliters will have to be 1, because if it was anything else, it's going to change that 1.84 given piece of information. So again, this is one piece. If we now go through to look at our solve, we're doing okay because we got grams in the numerator, which is what we want, but I have milliliters in the denominator. Well, I don't want milliliters, so what do I know needs to happen? I need milliliters to appear in the numerator so that it cancels. Ideally, I'm given just milliliters. So I go back to the question. Oh, look at my given information. I am given just milliliters, 1,275. Okay, milliliters. What's in the denominator? Nothing's in the denominator. Okay, but I can't put 0 because 0 does all sorts of bad math stuff. So 1 is the only thing I can place in the denominator to fix out that unit. What happens? The milliliters units cancel, and I'd be left with grams. All I've got to do is now multiply these two things by each other and get a final answer of... And when I enter it into the calculator, I get a whopping answer of 2,346 grams, which you should all be saying is the incorrect answer, because we have not accounted for sig figs appropriately. 2, 3, and 4. Why am I only allowed 3 sig figs? Because of the density given information. Multiplication and division, fewest number. The first insignificant digit is larger than 5. Add 1. My final answer is actually 2,350 grams. Note, no decimal point, which means that this 0 is acting as a placeholder and not as a significant digit. If we want to be extra clear in that, we could convert this to scientific notation. 1, 2, 3. 3 grams. It would be a positive 3 because we're at a number larger than 1. Okay? And that's how we could use density as a unit factor as well. Yippee! Okay, and with that, we move into a different topic, so I'm going to stop this recording.